Everyone, January 25th. All right, let's do this. Cheapest flights. Hit this fast. We really want to get into this one. We have an idea from yesterday, so we're going to try it today. All right, what's this? The cheapest flights within K stops and cities connected by some number of flights. You are given an array flights where flights I from to price. There is a flight from city from to city 2 with the cost price. You're also given 3 integers. Source, destination, and K. Return the cheapest price from source to destination with the most K stops. Oh, this is a very realistic situation. From start to end with the cheapest cost. So basically we have the start, right? We need an end, and we have the cost of each edge, and we want to find a route towards this with a most K stops, so K nodes in the middle. So this is kind of Dijkstra with a requirement. Okay, Dijkstra with requirement. How would you approach that if you do Dijkstra directly? I'm just thinking, if we do Dijkstra directly, it will probably trying to find the cheapest of flights. And then we say no, if we have more stops, then it's not possible. So we will just keep going. Yeah, we can try this if we do Dijkstra. I mean, the Dijkstra will be 0, 1, 1 to 2, and 2 to 3, because that's cost 400, right? But it has 2 stops. Let's see. I actually never given much thought to this. What if we keep Dijkstra going? What's going to happen? All right, so we do Dijkstra. We start with 0, and then the current we have 1. That's the only one it connects to. Oops. Then we have 100. So we take 100, and then we have the current cost. Right? And then from 100, we see the next destination. We have 2 and 3. Okay? 2 is 100, 3 is 600. And then according to Dijkstra, we're going to go to 2. That's fine. Yeah, well, that's fine. We can go to 2. And then we keep checking the current price. Not price, the current steps. Okay? So now we're at 2. So from 2, we can go to 100, and go to 0, 3. But we visited before, so we don't visit again. So from 2, now it's 2. From 2, we can go to 3. So about 2, we current the price is 200, right? To go to 2. And then to go to 3 is 200. So which means go to 3, we need 400. Right? So we have update. The 3 cost is 400 now. Okay? And then that's the first time we see 3, but the cost, the number of stops is 2 stops, because we count to reach 3. We take that much. So we say it's not possible, right, to reach there. So we probably don't even have to put this into the queue. So we just say not possible, and then we return. And then we return. Now in the queue is 3 with 600 pop up. So I think we just Dijkstra this thing, right? Dijkstra this thing. And but the path might not be correct, which means as you go on, you will be updating the price, right? You will be updating the price, and you need to know the previous price, right? Because now you have the current price. Let me think again. Now you have the current price, right? And then, because in Dijkstra, every time you go to the new one, you add up the current cost, and then you see if it's smaller, then you update the price, right? Update the price. So instead of updating the price, we have to, we can update the price and then try to see if it works. If it doesn't work, it will go back to some previous state, right? If it does not work, but all those have been already pushed into the hold on. So because every time you visit a new node, you will update its price, right? You'll update its price, and then you go down, and then if that's not right, then you will look back into the queue and you will pull out the previous thing. So I think, then you will pop those things out because those are not correct. Those are not correct. Or what you can do is find all the paths from source to destination that within a given requirement. You find those first. Okay? You find those first, and then you run Dijkstra in them. Then any path can work. Maybe that's a better way to deal with it, because I was thinking if you use Dijkstra directly and then you hit a price, right? And then you run Dijkstra to the end and then something doesn't work, then you have to unwind this whole thing, but you cannot unwind because you might already pop the price that's not correct, but next round you want to use it. So yeah, let's change this. How can we find all the paths leading from source to destination within the given K? So we just need to, we can DFS the whole thing from source to destination. That actually might not be a bad idea. We just DFS the whole thing and we can collect all the paths from source to destination, right? Yeah, let's think about this. You go, and every time you hit 3, every time you hit a destination, you get the result. You get the result and you get the number of paths. And then you just keep track. We don't even have the Dijkstra this thing. We just keep going. We BFS. We BFS. I mean, in this case, we can even DFS because we have a requirement, right? We have a requirement. Yeah. I mean, we can try BFS or DFS. It doesn't really matter too much, whichever we try. I think, I mean, if it's a DFS, we just need to check, right? If the depth is longer than K, then this path is not going to work. Yep. I mean, I might want to just do BFS. I will just do BFS, right? And then we'll stop. Yeah, I think it's just BFS, and then you might have multiple paths leading to the destination, and then just every time you hit the destination when it's good, and you just check the price. Yeah, I don't think we need Dijkstra for this, but it's a good way to think about it. So maybe next time we do have to do Dijkstra, we have an understanding of how Dijkstra will work. Alright, so here's the thing. We're gonna have, do we need to turn this into Gordy? Flights I is from and to, so there's no rule regarding this. Oh my god, I definitely don't like. Alright, so we need to do the graph. Right, default dict, which is fine. Graph equals default dict list. Okay, for A, B, P in flights. So it'll be graph A dot append BP. Right? Not append B, be A to B, and because it's a directed graph. Cannot go the other way. So once we're done, we're gonna say Q equals source. What else do you need? Source. I mean, steps can be on the outside, so it doesn't really matter. Then we just need source and price, right? Source and price. So this is gonna be, you know, source and price will starting will be 0, right? And then steps. It's not really steps. We're gonna call it stops, right? Stops are gonna be start with 0. Okay, so while Q temp for city, right? We're gonna say for city and the price in Q. When you say visited, okay, visited equals set, and then we say visited dot add city. Okay. Now we have its child, right? And then we also need res math.inf. Okay. And then we say for next in graph city. Okay. So the next come out. And then what we can say is yeah, we'll do it here. We'll do it here. What are we going to do? We are going to say if city is equal to destination, right? Then the price res shall equal to minimum res and price. And else we don't put anything. Else this one put in, right? And then we say, what do we say? We say for the next in if next is not in visited, okay, then we do temp dot append next graph city, and then also p next p, right? Next, and then current price plus p. Okay, once we done, stops plus equal 1, right? Q equals temp, so stops plus equal 1, and then we can do that will be the stop, and then the next one is if it hits, and then it's good. If we don't hit, then we have to do it here. We say if stops is larger than k, then we will break. Then we'll come out. Then we say if to return res, if res is smaller than math.inf, else return -1. Okay, that's a BFS. Basically just taking all the paths that's possible, and then we try to see if we can build it. $700. Oh, we have n as well. N equals 4. I guess you can do, I mean, it's all right. Yeah, all right. Yeah, all right. It doesn't matter. Same thing. Ooh, I need to include this one as well. 200. 500. Okay. And flights source test k. That was pretty bad. The hell happened? The first one is not right. Interesting. That means I never reached the destination. How? I have source. Yeah, the next and P. So yeah, so let's see what happened. Let's just print Q at each level. We got 0, 0. I got 1, 100. Oh, I did not continue. I did not continue. I go to 1. Yeah, 0 to 1. And 1 next is already 3. And then it's it, and then I just do this. And then, but 1 can also go to 2. But I already exhausted. So out of 1 is already equal to 1. Yeah, so we have 1, 100. So K is 1. Not K. Come on, stops. Right, so stops 1, which basically means when we visit 1, we have 1 stop. And for 1, I probably get 2. And then I get 3. How come I didn't get 3 from this? For city and price. That doesn't feel right. That does not feel right. So at this point, when visiting 1, it should be after I finish visiting 1. I get 1 stop, right? Now I'm visiting 1, I get 1 stop. Now while I'm visiting, this is the first stop. And then I go down, which means when I hit 3, that should be the second stop. So if this is larger than K plus 1, count the last one, then we are right. Wow, amazing. All right, so if we do this, fix the K, now we're right. So yeah, the problem is with the K. With the K. I mean, I could have started with like -1, then I don't have to do the. Oh. All right, let's try this. Oh, I got a wrong answer. That is very surprising. Oh my god. Okay, no panic. Let's see what the hell happened. 0, probably with a K again. Expected 40. All right, let's see what we have. 0 to 1, okay. 100. 0 to 2, 100. 0 to 3, 10. 1 to 2, Ooh, 1 to 2. 1 to 4. Nah, I see what the problem is. And 2 to 1. Oh my god. 2 to 3. 2 to 4. Holy moly. 3 to 2. 3 to 4. Ooh. Now what? We have so many connections that we can make. Damn. Huh. And we want to start from 0. Right, I want to start from 0 and go into 4. So start from 0. Want to go into 4. Lordy. 10. The answer is 40. And we can most 3 stops. I have to redo this. This is a very convoluted graph. Made me thinking it has to be backtracking instead of BFS. Because in BFS, we will visit the repeated visit the same node, right? Or, man, I don't think so though. I don't think so, because I added here, right? Hold on. 0 to 1, 0 to 2, 0 to 3. Okay, 1 to 2, 1 to 4, 2 to 1, 2 to 3, 2 to 4, 3 to 2, 3 to 4. Okay, now I fill in the price. We have 100 here, 100 here. 0 to 3 is 10. 1 to 2 is 100. 1 to 4 is 10. 2 to 1 is 10. 2 to 3 is 100. 2 to 4 is 100. 3 to 2 is 10. 3 to 4 is 100. So the going shall be 0 to 3, 3 to 2, 2 to 1, 1 to 4. That's 40. Okay, so what happened when we do the DFS? And then take a look. Let's get a queue and then take a look. So we start from 0, 0. Then the next level is a 1, 2, 3. Okay, so nothing's right. So the next round is going to be 4. We have a 4, but that's 110. So let's say, okay, that's not good. Next level is 4. And then, so 1 is not going to 2, because 2 is already there. So 1 will go to 4. And then for 2, 2 is not going to 1 because 1 has already been visited. That's why it's not going to work. And 3 is not going to 2 as well. So how do we BFS this? Or maybe we don't. I now think BFS is not the way to go. I think we need to do backtracking. Okay, like DFS, right? So if we do DFS and we keep track of the total depth that we go, and then every time the visited is only the ones we have visited on this same track, and if we backtracking, we can always revisit the node that have visited before. So no, I think this will now work. I mean, it might work, but I don't know how to BFS this. When you have, basically it's not a tree, right? It's a graph. It's a graph and it allows, then you cannot set, maybe you need to allow things to visit others on the same level. Okay, you need to allow visit on the same level. Hold on, allow visit on the same level. on the same level. So you always push this in. Hold on, maybe what we can do is we do it here. So we visit here. So we say if it's visited here, we say if city is invisited. Right, we'll continue. But then we don't check here. Still not work. But yeah, because you do from 2. Yeah, because you do 1 already. And then you do 2. Right, the next level you do 1. So I think what we need to do is if it's on the same level, right? So we have 1, 2, and 3. The next level, we can allow them to, yeah, maybe we shouldn't even bother with visited, all right? Because we are progressing and we have a limit, which is k, and if it's larger than k, we'll always stop. So we don't do any visited, and we'll visit more, but I think it will be right. So don't bother with visited. If we do not bother with visited, that might be right. So don't bother with visited. To allow the same, yeah, because it makes sense, right? So every time you visit something, and it's go level by level. So the next time you visit, it will be a different level. So that's a different path. So definitely you should not use visited. Unless this will go too slow. That seems to be the problem. Memory limit exceeded. Memory limit exceeded. The queue is too long. Let's try deck. I don't know. I mean, deck may be possible. It's not that much. Huh. I mean, this, we do have to hold 2 things, right? So a deck. Let's try a deck. And if memory, then we don't do this because that's what costs more. We can simply do this for this in range n. That would be the same thing, right? So will be a deck. Oh, q is equal to deck. Okay. And then stops res while q. Then we don't do this. And then we do city and price equals q dot pop left. Okay. If it is, res equals minimum. Else we'll say q dot append, next one. But when do we know? Right? When you do this, you do not know. Well, you know by you pushing in one more thing. I definitely do not like that. But I guess this is how we're gonna do. And let's do all of them in this. So that will be the level. Okay. Then we don't need stops because we're inside. So this is gonna be stops, right? And then we say if stops, right? So I add this stop. If stops is larger than k, right? If it's larger than k, we say break. Otherwise, you say if city is this equals destination, then we will do the current price. Otherwise, we'll try, and then we will do new thing, and then will be stops plus 1. Right, if stops is equal to k, that's still fine. And then no, it should be k plus 1. Right, that's k plus 1 still. Okay, and then we don't do this, we don't do this, we don't do this. Okay, let's try this. That still works. But the problem is this one. And I have to test it here. We should give deck. So a few measures that we are kind of alleviating the memory issue. See if it's gonna work. Looks not working. Memory, all right, that's okay. Let's this memory limit. This is a naive BFS. Memory is no good. Okay, so maybe we can try DFS. Try DFS, see what happens. Okay, so we try DFS. Let's try DFS with backtracking. We need a graph as usual. Okay, then we say def DFS. We'll have a city, right? We'll have the price, we'll have the stops. And this will, we actually not gonna return anything. So we can say self.res equals math.inf. Now we don't return anything. Say if stops is larger than k plus 1, then we return. Okay. Otherwise, if city is equal to destination, self.res equals minimum self.res price. Otherwise, and return. Otherwise, for next p in graph city, DFS next city price plus p stops plus 1. Yep. That's not really backtracking, just visiting all of them. So DFS city, the start source, price is 0, stops is 0, and then we'll return self.res. Okay, let's see this one. This one's working here. I mean, this should not have DFS, should not have memory, but it might be time. I don't see how time can be. Oh, so the naive also doesn't work here. I thought we can just, oh, yep, this one is time. Yeah, which is understandable, TLE. This one just switch time with space. Okay, so we need to be smarter. We need to be smarter. Okay. So I cannot use naive. So kind of have to opt for yeah, I was trying to think. So maybe I have to do Dijkstra anyway. But there's one thing in the Dijkstra that I haven't figured out how to deal with, because in the Dijkstra we'll dynamically change. We will change the actual price once we find a better one. And as we go levels over level, right? As we go level over level, and we build the price going down. Then what? I mean, if you think about it, in Dijkstra, you start, and then you find it's all its neighbors. You have all the prices. So you update all the price. Then you go to the smallest price. And from there, you go to all its neighbors, right? And if its neighbor is one of the one you visited before, then you'll update that price so you can get routed there. But by doing so, let's say you're routed there, okay? And it changes price. And the original price is still in the queue, in the priority queue. So you change it there. And then from there, you keep going, and eventually, oopsie doozy, we go out, right? We ran out of bound. And then if we go out of bound, which means we find the target, but we simply cannot continue, right? So we go there, and then we go out of bound. So now what? So maybe in Dijkstra, when you put into the priority queue, you also put into the current stop. How about that? You put into the current stop. Okay, let's say I do put into the current stop. But every time I visit something, I pop it out. I pop the node out. And now I do something. Okay? And then those nodes are forgotten. Right? Those nodes are forgotten. Like, it's just, you know, the performance is too bad. So that path is forgotten. So we go path, eventually lead to this, but it's too bad. And I need to basically trace it back to the first time when we hit it. Trace it back. The first time that we hit it. Because Dijkstra is actually not BFS, it's DFS, right? Just every time we pick the best node, and then if this node doesn't work, right? Because we have a priority queue, we pop the top, right? We say, okay, we go to this node, and then from this node we'll do, you know, whatever, and we need to push into the queue again so that we can pop out the best, right? And we're going all the way down. If it doesn't work, then we'll unwind. Then we unwind, which means the current best doesn't work. Then we can try the second best. How about that? We can try the second best at the moment. We can try the second best at the moment. So I pop it, and then we do. And then when we go back, but this thing is keep updating. The thing keeps updating. The queue, the priority queue keeps updating. So when we go back, it's not, the state changes. So I want to know at that moment, what are the, you know, the best next option. And if we go to the next level, well, we do only have 100 nodes, right? We do only have 100 nodes. We do only have 100 nodes. What else can we do? What if we copy? We copy the priority queue for each one. We just copy it. That seems to be a very stupid decision, because we will copy n flight's length. Now it's flight's length k. I didn't really say k is smaller than n, so at most you go 100 level deep. But then if it doesn't work, then what do you do? You unwind the previous step, right? You unwind to the previous step, but the previous step we have a global priority queue. Then we just prove that thing doesn't work. And you unwind. I mean, you will have all the previous worse steps all stored in it. But actually it's not even stored in it. Or maybe you can have another data structure that every time the price changes, you just append to it. You append to it. So once it's going bad, right? So in the priority queue. So once it goes bad, okay. Yeah, because in Dijkstra, every time you update, that must be through some other path. So when you update, it's your new price with the number of stops, okay? And with the number of steps that to reach you have a new value. So that's the new thing. And you can put in the priority queue. It's fine. Or not. It's also okay. And then you'll try that, right? You try that, and then you fail. Okay, you reach. You keep going. You don't reach. Right? If you can reach, if we run Dijkstra and then we reach the destination, everything's good. But if you keep going and you does not reach the destination, then what? Then I think what you need to do is to pop all of them. Pop that. Pop that. Pop that. So we keep a path, okay? We keep a path. Which means this path doesn't work. So pop the path, and then we need to see what is the second best, right? Second best at this current number of steps. Yeah, so we have the first step, we have these options, and I pick the best one. And then we go to the second stop. And the second stop, I have these new options, right? And they have price. And then we pick also the best. And then we keep going third, fourth, and then let's say at the fourth, at most the third, right? And then we go this, and then we do the fourth one. And in the fourth one, we don't find, and we go to the fifth one. Let's say k equal to 4. Right, and we go to the fifth one. We have fifth stop. We have a bunch of those, and then we go through every one of them, and then and then we go to the fifth one, and then it's already larger than. Then we return. So when we return, we go back to the fourth one, and in the fourth level, what we have done is that we popped the best at that level, right? we pop the best, because that's what we use to go to the 5th level. So now we know the best does not exist, so we can go for the second best. And then we try it. And if the second best doesn't work, we'll go to the third best. That might actually work. All right, let's Dijkstra this thing. Let's see how it works. All right, so let's Dijkstra this thing. Oh, maybe this is like A* search or something like that. I forgot how to do all those things. A* search. Anyway, so we need a list of priority queue. Holy guacamole. So import heap queue, right? So a list of priority queue. So we're gonna say heaps, right? Equals this. So each heap records price and node, right? Records price and node at the current number of stops. Okay, so if that's our case, then we can DFS def Dijkstra. So it'll still be a city, right? Will be a price, and then we need to know stops. Okay, if we do that, and if stops is larger than k plus 1, then we return. Probably also self.res equals math.inf. I mean, maybe for this we don't need to, because this is Dijkstra. So the first time we hit something, it's definitely gonna work. Yeah, because it's Dijkstra. The first time we hit, it will definitely work. And then we say if city is equal to best, now we just return. Ooh. Maybe this one shall return a Boolean value. We shall maybe return an integer. So bad is -1. This will just return price. So we know this is the right price. Okay. Otherwise, because we are in this stops, right? So what we do usually, is go for all of them, right? So we say for next price in graph city, but we need to know the previous price so that we can keep track of the current price. So do we also need a previous price? Then we can put into this. Then we can put into this the previous price. So for each one, we need to know its price at the current stop. Well, not the current stop, the previous stop. We need to know the price at the previous stop. So in that case, this is my current stop, okay, and I need to have a history of stops, and heaps is at each stop. We have a range of those, so we need another thing, because we just use heaps is not enough. Price history, right? And with 0, price history is just going to be 0 times n, right? That's the 0th stop. Actually, we can do this for this in range k. So we do k stops, right? Okay, that shouldn't be too big. And then, so for the next, and its price, we have the current stop. So like this city is the current stop, right? And we need to go to its current stop to see what price it has. What price it has. And what if it's not at a current stop? Wait, hold on. Because we go to the next city, right? That's the next city. No. So we can do p plus price, which is the price and the take to go to the next city. And then we want to know if it's smaller, if it's the best, basically. If it's the best, we don't really need to know if it's best. It's just going to be the price it's going to take right now to go to that city. Alright? Because every time we want to... No, because we were going to pop up when they use the other one. Oh no, this is not right. This is not right. Because the current price, if it's smaller than the other price, but if we only pop based on the history, that's not going to work. How could this be so hard? It's just Dijkstra with the requirement, right? It's a Dijkstra with a requirement on the number of stops, like how many edges, right? And within this amount of edges, what's the shortest path? Now, the shortest path, yeah, Dijkstra we're gonna pop out, no problem. But when you pop out, you also choose that route, right? So the question is, you choose that route and eventually fail, then you go back to the original state, right? You go back to the original state. How do you know where to go next? And you need to know the state, right? You need to know the state at each stop. That's what I think, right? At each stop, we have the next possible, right? We have the next possible, and then we know the current price. So we have the current price of reaching all these, and then we put all of this into the history of all of them, right? The history of all of them, and then we need to say, okay, then where should I go? And then they say, okay, we have something that happened previously is smaller, right? So we add them all to the heap, and now we, boom, something previous is actually better. So the next one we actually go there, right? And that will really rewind the history to the previous one, right? So we go there, okay, and I would take that one out, and then and as we go, if something that's previous in it, but the price is different, so those things will be popped, right? We don't care about them anymore, but they're actually needed, right? They're actually needed. So I don't know, maybe we need to sort it, and but if we sort it, then we cannot pop it. So we cannot throw them away. So we can pop them, put them into another queue. Okay? Yeah, anything we pop, we put in another queue. We pop, put in another queue. And then we'll find the next one. And then that will be the route, right, towards something. And then boom, it doesn't work. Right, if it doesn't work. And we know its path. And if it does not work, then what? And we have something in there. We can pop all of them into this and find its smallest. And the sides, we're gonna go from there. So basically the best one doesn't work. Then we're gonna go from the second best. Right? Basically that's the second best. But if that's the second best, how do you update the price? So how do you know, right, what is the current? Man, I don't know. I don't know. Memory. Yeah, that's what I have. I'm also thinking we can go Dijkstra once, right? And then we change. Oh, what? You keep the suboptimal, you don't throw them away. You keep the suboptimal. And then if you pop it out, that means through some path, you can reach this with that price. Okay? And because that's the smallest right now, you say, okay, I will just start from here. And from there, you can, you know, reset everything. Okay, you reset everything, and maybe, yeah, you can reset everything. Hold on, prices. I have to do mass.inf. Times n. We still use one heap. Oh, we need to use two heap. Heap 1 and heap 2. Heap 1 and heap 2. That sounds ridiculous. But that's how I see it right now. So I have two heaps. And then we do Dijkstra. Okay, so Dijkstra basically is we'll do heap 1 as a source. Okay, we put a source in it. Source, price, and stops. Okay, and then we'll pop. Now price should be the first. Price, source, price, city, and stops. Okay. Then what? Then what we're gonna say is from the source we are going to price source. We're gonna say prices source is gonna be 0. Okay. So from the source, we're gonna say while heap 1. Okay. While heap 1. Price city stops equals heap q dot heap pop heap 1. Okay, we get a city and we get a stops, and then we need a handle if stops is larger than k plus 1. What do we do? Okay, and then at any time we say if city is equal to destination, then we shall just return price. I think that's right. Otherwise we need to go for next price in graph city, right? Then we need to say if it's smaller than the price, then we update the price and we push this into the heap, right? Then we say if price plus p is smaller than prices next, then prices next equals price plus p. And no matter what, we're gonna push this into the heap queue. And then we say heap queue dot heap push, right? And the heap 1, I'm gonna push what into it? We're gonna push I'm gonna push price plus p, the city, and the stops plus 1. Okay, so we push into the heap 1, and then we update this. Now this one should be while heap 1 0 0 if the price is larger than prices, which means it's the old one, prices heap 1 0 1, right? Because the current the top of the heap is larger than this. I mean, we should not use this one because that's not updated. Then we just say heap q dot heap push heap 2. We'll pop this. We just push the heap q, push the heap q. If it doesn't fit the prices until the one that's not, then we'll jump out, right? And then we'll jump out. We'll get the current one, which is correct, and then they will do blah blah blah, and then we'll push it in, and then we can keep going. Okay, no problem. And heap q heap push will push everything in no matter what, and then we'll get back. All right, once this is all done, we go back to the top. Heap 1 blah blah blah. If stops is larger than, which means the current is not gonna work. So everything in heap 1 needs to be pushed to heap 2, and actually we don't have to push everything to heap 2. If the currents stop, then we can just disregard heap 1. We can just say if this and we just say heap 1 equal to heap 2, right? Because we have all the thing that's dumped, right? Dumped from heap 1 initially, and then we captured it by heap 2, and we'll just use everything that heap 2 currently has, and anything remaining in heap 1, they all have. Actually, that's not true. That is actually not true. We need to put everything in heap 1 to heap 2 whose stops is, smaller than k plus 1. That makes sense? Because they still have a chance, right? They still have a chance. So we can say while heap 1 price city stops equals heap q heap pop heap 1. So we pop everything. If stops is smaller than k plus 1, which means by plus 1 we can still do, right? Then heap q dot heap push heap 2, price city stops potential, because these are things we can reach, right? So blah blah blah. Once we're done, heap 1 equals heap 2. We swap this, and heap 2 go back to this, and we'll continue, right? Then we go back to the top. Oh, then we also have to reset all the prices, right? We'll reset all the prices. We'll reset all the prices. Shall we reset all the prices? That's a good question. We start fresh, right? We start fresh. If there are some prices earlier, and all of those are the prices affected by the first round, and the first round, if it's not right, then we do have to reset them, because they're all, coming from the first round. But there are prices we should not reset. I don't know. Prices we should not reset. You know what? I want to redo the DFS. You know what? Let me redo the DFS. Wait, hold on this. We didn't do the visited thing. We did not do that. I don't know why we didn't do that. Right, or city visited, we return. Right, if city equals this, we do this. Otherwise, we can say visited.add city. So each path going down is always unique. All right, but next, I don't know. Let's try solution 2. 89. Yeah, I know. I'll just comment on this. Oh, more. Oh, we forgot to put visited. And at the end, visited dot remove city. Maybe. Who knows? Try this. So not falling back into a cycle, but doesn't Doesn't look like that's gonna be the way though. Nope. Yeah, still TLE. Alright, so we'll go back here. Okay. I want to know what price, what things, I mean, we can try reset the prices. Okay, we can reset the price because it's almost as if we are redoing everything, right? We're redoing everything, and then but there will be things that you might visit that will cost a little bit more. I don't know. Shouldn't the original be changed? And if we continue, and all the pricing will be negative, then we'll take out the first one, and then we will put everything to this. Let me just try. Let's just say prices equals, yeah, we'll redo this. Then we'll continue. And then have return here, so eventually we'll return minus one. Not sure. This is kind of very rushed out of range. Okay, while heap one. Oh, so we pop everything out. This is the first one. Now we have an issue. The hell? I popped everything. Oh no, we have nothing in heap one. Well, heap one. Yeah, we popped everything. There's nothing in heap one. Which when we keep popping, I'm going to heap two. The hell is the situation? Heap one is 300 as a price. City is, wait, what? City is 0. What? How is city 0 as 300? Because you go back to 0. You go back to 0. So it's 0, 0, 0, and I'll have 101. And then it will be 202, 2. And then with 300, 0, 3.
Maybe your mom saw Jamba and got mad.
That is not possible.
Really?
I don't think so. It was easy. No, 400. We have 400, 3, 3. And we also have 300, 0, 3. And then 303, we got pop. And then we have 732. 700. 700 is this, right? And then 732 gets popped. And then let's no, this one's go out first. But it's bigger, so it goes to push to heap 2. Next one's 433, okay? And then 433. Let's see. Okay, after this, heap 1's 433 and 732. And then go here, 433. 3 is larger than, so it's not gonna work. And then say, well, heap 1, I have 732. Okay, and then we push 732 into heap 2 because that's 2, right? It's smaller than smaller than 1 plus 1. I shall push it in. Yeah, smaller equal to, and I shall push it in. All right, and then this one works. But we still have the issue, right? It's we can keep pop and nothing, and then we should say if not heap 1, I say if heap 1, if not heap 1 or heap 1, right? And heap 1 0 2 is larger than k plus 1. When that happens, we do this. Otherwise, we do this. How about the others? Okay, they all pass. This one work? Ooh, this one seems to be working. All right. Let's see. No. Either wrong or time limit. Oh. Well, we got much later than before. 37. Previous memory is 28. Dude. Oh, it's not this one, time limit. This one I think is... Actually, I'm not sure. Let's try this. Loop. Forever loop. Holy guacamole. I mean, we should add visited, right? We shall add visited, but yeah, so every new thing coming in. What is this? 0 to 3, okay? 0 to 2, 2 to 0, 0, 3, 2 to 0, 2 to 3, 0 to 2, 3 to 1, 1 to 3. What the hell? Start 3, and then we want to go to 0. There's no path. Start from 3. So 3, 2, 1, 1, 2, 3, 3, 2, 1, 1, 2, 3, 3, 2, 1, 1, 2, 3. Alright, we need a way. But how? So it should be on the path. So in this case, 3 go to 1. Right? Okay. 3 go to 1. Because 1 is the next one. And then for 1, we have only 3, but we are on the same path. So it shouldn't do. Then that's it. That should be the end. Which means, but if we go through all the paths, which is fine, and now we unwind to a certain point, and there are things I don't know. Alright? We don't know which one has been through. Damn. You should, like, we need to put a record. Previous. Right? We need to reconstruct a visited using previous. Reconstruct. Oh my god. Yeah, because like the next path we can lead up to the previous, and then we have a circle. We just start circle. Oh, it's fine if we restart circling. It's okay, because we'll build a new visited. Okay, so we need a visited. We do need a visited, which is a set. Okay. Blah blah blah. If blah blah blah. Oh, and then we say visited. Reset a visited. Right. Otherwise, we do this. And then we say visited.add city. And then for next, do we handle this? That's a good question. Do we? It's on this path, so it should not be included in this. It's like something, the next one go here. So we have a price for going here, but there's always going to be higher price. So we shouldn't even include. Which means we might not even need visited. If we just do this. But if we do this, yeah, it has to be smaller. Then we add. Hold up. What if we don't? It should still be right. I don't think we need visited. And then we refresh the prices. That means if you visit again, you're always going to be a higher price. Exactly. So if we try this again. Okay. One more time. Oh, we passed. Oh my god. Oh my lord. At least solve this time. I started feeling, uncomfortable again. That's exactly how I feel the other 2 days. Dear lord. This is a very convoluted implementation of Dijkstra. Alright. Basic idea is to Dijkstra once. If we hit source within case stops, good to go. We're good, right? If not, we basically reuse all the previous cities, right? All the previous unused cities to run Dijkstra again with sub-optimal choices. Now to enable this, I use 2 heaps, with heap 2 always collecting the suboptimal choices popped by heap 1. And once heap 1 is no-go, right? Heap 1 is no-go, we swap and go again. Yeah, that's basically how it is. I forgot the runtime of Dijkstra. Alright, well, stop right here, and I need to read the solution. Oh my god, this is hard. I'm pretty sure I'm doing it the wrong way, but hey, solve is solve. Alright, I'll see you guys tomorrow. I'll read this. Adios.